So here we have an example. A ball is hit straight up in the air with a displacement formula of x equals 40t minus 5t squared. Now, as soon as I look at that, I've got to picture what type of graph this is. The highest power of t is 2, or it's squared. So this is a parabola. And even more than that, that minus 5t squared tells me that it's an upside down parabola. Now, don't be confused into thinking that if I have some kind of parabola, that this is a picture of the flight of the ball. The ball's not going through the air from one point to another. It's going straight up and coming straight back down to where it landed. But as we look at time, we can see the height that it gains. Remember that. Now we've got a few things to do. We need to graph displacement, velocity, and acceleration. Now, if we're asked for velocity and acceleration and we're not given that word average out the front, they mean the instantaneous velocity and acceleration. So we're talking about using calculus here to find the exact velocity at any one moment in time. What was the initial velocity? So that was the velocity when time was equal to 0. How high did the ball go? And how long was it before it hit the ground? So we need a length of the flight in seconds. Okay, so the first thing to do then is we need to graph all three functions. So first, let's go ahead and find all three functions. Now, I'll do my working for A over here, just so I've got plenty of space on the board. Now, I could graph this straight away like this, but the easiest way to graph displacement, I think, would be if I converted it into a factorized form. Now, I can bring 5t out the front of some brackets. That leaves me with 8 minus t inside the brackets. That's a lot easier for me to graph because if I let x equal 0, I can see that I'm going to have an intercept with the t-axis at 0 or 8. So that helps me draw that really easily straight away. I've got time here and I need to put that on my axis, and I'm going to go up to 8 because I can see that that's what I'm going to need, and there's an intercept there. And then on this axis, which remember is x, we have x on the y-axis, a little bit confusing, and t is on this axis here. So on the vertical axis, we've got displacement. So write that down so it's really clear what your graph is showing. And now I need to graph this. Now I can see that I've got intercepts here and here, and I can also see that it's an upside down parabola. That's enough for me to rough in some kind of shape here. Now, when it comes to finding this point, you've got a few skills. You'll need to go right back to year 11 and look at your skills that you have with parabolas. We can find the axis of symmetry a couple of different ways. The most logical way here is just to average the x-intercepts, or the t-intercepts in this case. So I can see that this is going to happen when time is equal to 4 because it's literally halfway between 0 and 8. But don't forget, if you have your formula in the form y equals ax squared plus bx plus c, then the axis of symmetry would be minus b over 2a. Now ours isn't in that form, so if we're going to use that method, it'd be quite slow. We'd have to rearrange it. I'd say x equals, because don't forget, x is what we're putting on the y-axis now, so it takes its place. We'd need to put the t squareds first, plus 40t. So now we've got it into that form. The axis of symmetry should be minus b, which is minus 40, over 2 times minus 5, which is minus 10. And sure enough, negative 40 divided by negative 10 is equal to 4. But see how I worked that out much more simply just by averaging the intercepts. Saved me a lot of time and all of this board space and effort. So now I've got the axis of symmetry. If I plug in t equals 4 into either version of this equation, let's plug it into this one, I'll be able to see what this high point is, and that will make my graph nice and complete. So 5 4s are 20, and 8 minus 4 is 4. 24s is 80. So I'm going to go ahead and put 80 on here. And that's enough. I've got my 4 and my 80, so I've sort of labelled everything. All right, the velocity, I'd better differentiate displacement to find the velocity formula. Then I can graph it. Now, I could differentiate this, but I'm going to need the product rule for that because it's got two parts, both of them with t in it. It's going to be much easier to differentiate this version one term at a time. So v is equal to, let's differentiate here with respect to t. We get 40, and differentiating here, the 2 comes down, we get minus 10t. All right, now if I asked you to graph y equals 40 minus 10x, you could easily rearrange that and say it's minus 10x plus 40. We can see that that's a straight line and it's got a y-intercept of 40 and a gradient of minus 10. Well, that's exactly what we have here, except that we need to just move things around a little bit. We're not graphing y, we're graphing v. And we haven't got x there, we've got t, don't we? Now, the reason I put the x's and y's there was not to confuse you. Where's the x gone and where's the y? It's just that we need to get used to knowing taking our skills that we had with x's and y's and knowing what straight lines and parabolas and things looked like, to working with t's and v's and a's and x's and recognizing it's the same thing. I've got to graph v up here and label it as velocity. And then I've got t down here. In fact, that's not the x-intercept at all, is it? It's the v-intercept. Silly me. Okay, so now I've got a straight line. My v-intercept is 40, so let's put that up here. And I've got a gradient of minus 10. So that's very steep, isn't it? It's going this way, and it means for every one square across, I'm going 10 squares down. So if I go 40 squares down instead of 10, I'm going to need to go 4 times as far across. It will be 4 squares across. And that tells me it's going to go through here when t equals 4. So my graph is going to look like this. Now, does it keep on going down? Can it go down? Can velocity be negative? Well, yes, it can. Let's think about what we know over here. It makes sense that when time is 4 seconds, the velocity is 0, because we've just seen that at time 4 seconds, that's when the ball gets to the highest point it's going to get to. And we've already thought about the fact that at that point, just for a moment, it'll be stopped. Makes sense. Now remember that velocity takes direction into account. So as this ball is travelling downwards again, remember it goes straight up and then straight down, the velocity will be negative as it goes down, because the displacement, it tells us that the displacement is decreasing. We're going from a high point to a low point, so it's going down. So the velocity is actually negative too. So you can graph to here, but it's important that you keep on going. Now, how far do you keep going? Well, I'd keep on going all the way until time is equal to 8, because it seems to me that that's where the ball hits the ground. And so we're going to have that point down there. Now, this is a straight line, so the gradient is going to stay. So this distance and this are the same. So this height is going to be the same as the negative height that I have here. So this point down here by rights should be minus 40, and I can label that. All right, next we need to graph the acceleration. So let's come up with a formula for it first. We need to differentiate v with respect to t. So the 40 we can leave out, we just get minus 10. Well, that's a very simple graph. We have t down here, we have a up there, we should have written time here and here. And this we can label as acceleration. Now, straight away, you're probably noticing I haven't made my y-axis very well. It needs to go down to minus 10. And all we need to do is a straight line coming across here at y equals minus 10. Not y, but a. I'm sort of using this as my whole idea of what the line y equals minus 10 looks like. Because the acceleration is minus 10 for the whole time. Okay? Now we've done part A, graphing the displacement, the velocity, and the acceleration. All right, part B, what was the initial velocity? Well, initial means when t equals 0. So we've got a formula now for v. We can just plug in t equals 0 and we get 40 minus 0 is 40. So that's very quick and easy to answer once we have our formulas. How high did the ball go? Well, we've actually already thought about this. It went up to 80 metres. And how long was it before it hit the ground? Well, it seemed to hit the ground again at 8 seconds. Now, with a question like this, a lot of your working might be done for part A, but once you have your formulas and even your graphs done really well, a lot of the other questions can be answered quite simply and easily. Now, with these sorts of questions, remember that the highest power of t should decrease by 1 in each differentiation. So always look at your three formulas for displacement, velocity, and acceleration and check that they make sense. If you have the opportunity to differentiate one term at a time, take it, because that's always the easiest way to do it. But you might want to factorize something just for the ease of graphing it and understanding what it means. So for an example like this, we've got a cubic curve for displacement, and it's a positive one, so we know it's going to have some sort of shape like that perhaps. That means that velocity will be the shape of a parabola, and acceleration should be linear or a straight line when we graph it. So differentiating this one quickly just for practice, we'd get 3 comes down, so we've got t squared minus 12t plus 27. Sure enough, looks like a parabola. And we could factorize that, we could use the formula or complete the square, any of those skills to graph it and to work with it. For the moment, let's just make all three formulas. This one would be 2t minus 12. So then we know that this is a straight line with a gradient of 2 and an intercept of minus 12 on the vertical axis. We'll say a vertical intercept rather than a y-intercept because we're not really dealing with y's here. We would have a on our vertical axis.